For this afternoon, our topic will be all about traffic route assignment. So what is traffic route assignment? So this is the process of allocating given set of trip interchanges to the specified transportation system. So before anything else, this traffic route assignment is one of the four-step transportation forecasting models. So the fundamental aim of this traffic assignment process is to reproduce on the transportation system the pattern of vehicular movements which would be observed when the travel demand represented by the trip matrix or matrices to be assigned is satisfied. So this traffic assignment is ginagamit sa nato ni siya to estimate the traffic flows on a network. So these models take as input a matrix of flows that indicate the volume of traffic between the origin and the destination. So what are the major aims of track assignment procedures? So first, we have to estimate the volume of traffic on the links of the network and obtain aggregate network measures. Second, to estimate interzonal travel cost. Third, to analyze travel pattern of each origin to the destination, the O to D pair. And fourth is to identify congested links and to collect trace data useful for the design of future junctions. And so, para mahimo nato ang trip assignment, we need these datas. So, unsa man kayo ang mga data na kinahanglan nato? So, first, we have number of trips that will be made from one zone to another. So, kani siya nga information ato ni siya makuha or atong ma-determine gikan dito sa trip distribution phase or katong the second step sa transportation forecasting model. Then the second one is a description of the highway or transit routes between zones. Ikatulo is the travel time on each route segment. So importante jud kay nato mahibaw-an nato kung unsa kadugay ang pagbiyahe ana nga adalan. And then the fourth and the last step is the last data that we need is the external trips that were not considered in the previous trip generation and distribution steps. So katong mga wala na consider dito sa the previous steps, diri nato na siya kinahanglanon kaayo. So karon natay basic approaches. So tulo ni siya kabuok, and the basic approaches that can be used for traffic assignment purposes is naatay diversion curves, nasa tay minimum time path assignment or also known as the all or nothing. Then apud tay minimum time path with capacity restraint. So karon ato na siyang isa-isahon. So first, let's tackle about the diversion curves. So unsa man ang diversion curves? So diversion curves method is similar in approach to a mode choice curve. So kung nakabalo mo dito kung unsa tong sa mode choice, similar ni siya dito. So the traffic between two routes is determined as a function of relative travel time or cost. Okay, now let's move on to minimum path algorithm. So, kaning minimum path algorithm, this is the shortest path algorithm. So the shortest path algorithm calculates the shortest path from the start node to each node of a connected graph. So the minimum time path method assigns all trips to those links that comprise the shortest time path between the two zones. So the minimum path assignment is based on the theory that a motorist or a transit user will select the quickest route between any O to D pair. So syempre, kung ikaw motorist or transit user, mas gusto gyud ta nga madali ato ang biyahe. The results can be depicted as a tree. Ato ni siyang gitawag og scheme tree. So all trips from that zone are assigned to links in the scheme tree. A node in the area-wide network represents each zone. So the algorithm that will be used in the next example is to connect all nodes from home, so kung siya gikan, and keep all paths as contenders, and until one path to the same node is faster route than the others. So, ato na siya ikunik-kunik gikan sa home, padlong sa imo ang zone na padulngan, and then, kung asa ang route na mas paspas, mo to siya mapilian. And at which juncture, those links that are slower path are eliminated. So, kung asa tong path na mas dali, mo to'y magpabilin. And then the slower ones, mo to siya mga eliminate na to. To solve this, we have a general mathematical algorithm. Ang atong formula is summation of Vij times Tij from all Ij, where Vij is equal to volume on link Ij and Tij is equal to travel on link Ij, and Ij means adjacent nodes. Okay, example 12.8. So, finding the minimum path in a network. To illustrate the process of path building, considered the following 16-node network with travel times on each link shown for each node or zone pair. Referring to the illustration above, the link on the node network is representative of the road and street system. So determine the shortest travel path from node 1 or home node to all other zones. Now, unsaon nito siya nato pag-solve? So, natay solution. So, step 1, we need to determine the time of the nodes connected to the node 1. So, ato yung tanawon kung pila ang time. Time to node 2 is 1 minute. Natay 1 minute, lang to sa node 2. Time to node 5 is 2 minutes. Times are noted near nodes in diagram. So, step 2, from the node closest to the home node, kung node 2 is the closest to home node 1, katong node 2 mo may kinadulad sa ito ang home node, make connections to the nearest nodes. These are nodes 3 and 6. Write the cumulative travel times in each node. So, step 3. So from the node that is now closest to the home node, or katong node 5, make connections to the nearest nodes, matumutang nga din og node 6 and 9. Write the cumulative travel times at each node. Ay, kalimti o sulat ang time. Let's proceed to step 4. So, time to node 6 via node 5 is shorter than that via zone 2. So, kay mas duol man ang via node 5, therefore, link 2 to 6 is deleted. Step 5, 3 nodes are equally close to the home node, katong node 3, 6, and 9. So select the lowest number node, which is the 3, and then add corresponding links to the node 4 and 7. Step 6, of the 3 equally close nodes, node 6 is the next lowest numbered node. So connect to zone 7 and then i-eliminate na to ang link 6 to 7. And then after naana niya, sa ato ding step 7, building proceeds from node 9 to nodes 10 and 13. Then, eliminate link 9 to 10. And then step 8, mag-build na pud kaog from node 7. And then sa step 9, dito ka mag-build from node 13. And sa step 10, mag-build ka from node 10 and then eliminate link 10 to 11. And then step 11, build from node 11 and eliminate link 11 to 12. And then step 12, build from node 8 and eliminate link 3 to 4. Then step 13, build from node 15 and eliminate link 14 to 15. Then step 14, last step na to, build from node 12 and eliminate link 15 to 16. So that's it. Yan, ito siya ka-easy na to pag connect sa mga nodes.
Good day everyone. So today we will be talking about capacity restraint. So, a modification of the process just described is known as capacity restraint. Using relationships between volume and travel time or speed similar to those derived in chapter 6, it is possible to recalculate the new link travel time. A reassignment is then based on the new values. The speed-volume relationship most commonly used in computer programs was developed by the U.S. Department of Transportation and is depicted on figure 12.14. It is called a link performance function. No. It is expressed in the formula which is T equals T sub 0 close bracket 1 plus 0.15 times the quantity of V over C to the fourth power, which is T is the travel time on the link, T sub 0 is the free flow travel time, V is the volume on the link, and C is the capacity of the link. So, the capacity restraint relationship given in equation 12.13 can be generalized by allowing the coefficient to be adjusted to corridor specific or roadway type as follows. So, we have T equals T sub 0 close bracket 1 plus alpha times the quantity of V over C to the raised to the power of beta. So, T is the travel time on the link, T sub 0 is the free flow travel time, V is the volume on the link, and C is the capacity of the link. Alternatively, a traffic engineering study can be conducted for a specific corridor and a model fitted to the collected speed and volume data to determine the appropriate values for A and B, as shown in the figure. So this is the figure of travel time versus vehicle volume. So we have a table of 12.25 which is roadway types specific parameters for capacity restraint. So example uh, example in computing capacity restraint travel times. So the volume on the link 1 to 5 was 485 and the travel time was 2 minutes. If the capacity of the link is 500, determine the link travel time that should be used for the next traffic assignment iteration. The solution is T sub 1 equals T sub 0 close bracket 1 plus 0.15 times the quantity of V over C to the fourth power. So, T, using the formula above, we have T sub 1 to 5, which is the link, equals to 2, which is the travel time, close bracket 1 plus 0.15 times the quantity of 485, which is the volume, over 500, which is the capacity of the link, raised to the power of 4. We got 2.27 minutes. So, the link travel time that should be used for the next traffic assignment iteration is 2.27 minutes. That's all. Thank you.
Total system cost assignment. Application of equation 12.12 in conjunction with the equation for capacity restraint, equation 12.13 will result in an equilibrium assignment where no single user may reduce their individual travel time by changing travel paths. However, user equilibrium assignment is not necessarily the method that results in the lowest total travel time for all travelers. Example: to illustrate the potential benefits of a system cost assignment, consider a simple highway network shown in Figure 12.15. In this situation, there are two origin zones, 1 and 2, and one destination zone 3. The travel times for each link can be given by the following relationships. Travel time sub 1 2 is equal to 3 over 1 minus volume sub 1 2 divided by 10,000. Travel time sub 2 3 is equal to 3 over 1 minus volume sub 2 3 divided by 800. Travel time sub 1 3 is equal to 12 over 1 minus volume sub 1 3 divided by 100,000. As shown below, Only those traveling between Zone 1 and Zone 3 can reduce driving time by changing routes. In general, the assumption of user equilibrium assignment is a more realistic basis for depicting individual decision-making since travelers act on what they consider to be their own best interests. Example: capacity restraint for a more complex network. In this network, there is just one origin zone, Zone 1, one destination zone or Zone 2, two intersections shown as 3 and 4, and 5 unidirectional links designated as L13, L14, L32, L34, and L42. For the network shown in Figure 12.16, A. Write the general capacity restraint relationship if A is equal to 1 and B is equal to 2. Compute the cost of travel for link L13 if B13 is equal to 30. Identify all possible travel paths from Zone 1 to Zone 2. Perform an equilibrium assignment. Remove the appropriate constraint to perform a system optimal assignment. In Figure 12.17, a deterministic user equilibrium assignment in Excel or starting point. Below Figure 12.17 is the result of deterministic user equilibrium assignment. And that's all. Thank you.